As of now our understanding is there is a CPU and there is a split cache, so L1I and L1D, and then there could be a unified cache which we call it as the L2 cache. Okay. So structural the way why we had a split cache was that there could be structural hazard, and if there is no split cache, and so for that reason we just basically made this as a I and this as a D. And from a security point of view, please also note that this I cache can be made in such a way that from the CPU point of view it can be only a read only cache. Okay, because you are going to only read the instructions. CPU is not going to, unless we have a notion of what we call as rewriting codes. This is a concept where when the program is in execution it will decide on what, it itself will generate a code and it goes and executes. Okay, there are some interesting problems that we can solve using rewriting codes. Just have a look at it. It's more of a POPL principle of programming languages type of concept, but just I am giving you a small pointer to that. Okay, so unless it's a type of a rewriting code, right, you are only basically going to read from the instruction cache. So from the CPU point of view I can make the instruction cache read only. Well, there will be update. So now this is a set. So let us do some small numerical analysis. Let us say that so what is AMAT? What is AMAT? Average memory access time is what? L1 cache access plus 1 minus heat at L1, heat ratio at L1 into miss penalty, correct? We derived this, do you remember? How did we derive this? Raghav? What probability? Heat ratio into L1 cache time plus miss . Okay. So for all HL1 is the hit ratio into for all those fraction of those instructions will take L1 cache time, access time. The remaining will take L1 cache plus miss penalty. Miss penalty is the time required to access anything beyond L1. Now this basically gives you H of L1 into L1 cache, or we can have it as miss ratio M of L1 plus M of L1 into L1 cache plus M of L1 into miss penalty, whatever MP. Okay. So this actually becomes L1 cache, while this becomes 1 minus HL1. Okay. So this basically gives us a recurrence equation. So I can now go L2 cache, L3 cache, L4 cache and so on. Okay. Okay. Now let us say L1 cache time, can you guess? Let us say 10 nanoseconds. Okay. And hit ratio let us say 96% or 0.96. Even this is not good, okay, right, in real sense. Okay. Now memory access time, memory actually RAM, guess, huh? Milliseconds, kya milliseconds? Say 100 milliseconds. Okay. So your average memory access time would be 10 into 10 power, let us make everything as 10 into 10 power 9 minus 9 plus 0.04 into 10 into 100 into 10 power minus 3. Okay. So this will be 10 power minus 8 plus 100 is 10 squared, right, by 10, 0.04 by 10, which is something like 0.004, correct, this one around. Okay, so I can still have it as 10 plus 10 into 10 power minus 9 plus 0.004. Okay. Okay. So, which is dominant here? This is still dominant. You are getting this, right? Even though I have this is 100 millisecond and this is 10 nanoseconds, please note that this is still very dominant, right? Your 0.004 comes in, whatever you say 4 milliseconds, your average memory access, if everything is fetched from memory, it is going to be 100 milliseconds per fetch. But since I have cache, I have reduced it from 100 milliseconds to some 0.004, that is 4 milliseconds. I have got 1 by 25th, our speed up is 25 times, right, by Amdahl's law. You all remember Amdahl's law, right? Okay. Speed up now becomes, oh, I thought I should ask one question in Amdahl's, forgot. Okay. N semi-loss. Okay. So, 0.004. Okay. So, what does this teach you? This teaches us that in spite of having 96% cache hit, we are not able to actually, we are not even close to the cache access time in terms of average memory access time. So, something like 0.99 or 99% is what that could be, giving us some amount of relief. So however good your cache may be, right, cache has to be very good. Your replacement strategy plays a very big role. Okay. Towards the end of this course, last week I will teach you about this cache replacement policies, like how we can implement hardware for cache replacement. It's slightly very advanced and we will basically take it up at that point of time. Okay. If we have time, we will do that. Okay. But whatever good your cache thing would be, right, I have to have a very good hit ratio, and in spite of having a very good hit ratio, memory still holds the between these two components, memory still holds the major factor, right. So, this in the Excel sheet, this 10 power 10 into minus 9 will never even figure. There will be some one very far off, right, in Pondicherry. Okay. So, right, so we can't even see that one here. So, that's the basic thing, and that is why, and these are somewhat realistic figures. I'm not saying these are the realistic figures, but you can work out, you can go and look at Wikipedia and it will give you how the cache speed has increased, how the memory speed has increased. But overall, this is something that we could see. Now, the way by which I could reduce this 0.004 still better is to have the L2 cache, and that is the reason why we go in for the L2 cache. So, in the context of L2 cache, what will happen? Now, let us go to the L1 plus L2 cache now. Let us see. So, let us say L1 is 10 nanoseconds and some 0.97 is its ratio. Now, L2 is larger in size, and L2 is a unified cache. What do you mean by unified cache? You do not distinguish between instruction and data. Okay. So, it is a large cache. So, let us say it is going to say something like 100 nanoseconds, and its hit ratio is some 0.98. It will be certainly more than this. Okay. Then of course, memory, now let us say this is going to be same 100 milliseconds. Right. Our earlier thing was 10 into 10 power minus 9 plus 0.004 was our earlier thing. Okay. I am using the same L1, same memory, but I am just introducing an L2 cache. Now, what will be the equation for this? AMAT for this would be L1 cache plus L1 miss ratio, miss of L1 into miss penalty would be what? The same thing, L2 cache plus miss of L2 into RAM access time. Okay. This is a recurrence equation, right. It is the same recurrence equation. Instead of miss penalty, I say I will access L2 plus miss of L2 into whatever RAM, right. Do you follow how I am getting this equation? I just explained in the previous class also. Let us substitute here. L1 would be 10 nanoseconds, 10 into 10 power minus 9, plus miss ratio is 0.03. Oh, I just put 0.96 right last time. Okay, I will have that same thing. 0.04 into 100 into 10 power minus 9 plus miss of that is 0.02, okay, into 100 into 10 power minus 3, okay. This is the thing. So, let us see, this is 10 power minus 8 plus 100 into 0.04 is 4, 4 into 10 power minus 9 plus 0.04 into 0.02 is 4, 4 into 2, 8 into 10 power minus 4 into 100 into 10 power minus 3, okay. So, this is 14 into 10 power minus 9 plus 8 into 80, 80 into 80 plus 80 in 8 into, so this is 100 is 10 power minus 10 power 2, so 10 power minus 1, 8 into 10 power minus 5, okay, right. So, you get 14 into 10 power minus 9 plus 0.00008. Okay. So, let us say these two are almost comparable, okay, but what would have happened is this 0.004 actually became some 1000 times faster, right. So, this is 4 into 10 power minus 3 and I have something like 8 into 10 power minus 5. If I divide this, okay, I should divide other way, right, 4 into 10 power minus 3 by 10. So, this goes 2, so this goes 10 squared, 0.5 into 10 squared or 5 into 10, 50 times faster, okay, 50 times faster, okay. So, if it takes, imagine, right, a program taking 50 hours will now take 1 hour, right. That is the way you should look at it. What it means by 50 times faster is, so suppose the unit is 1 hour, then if the program takes 50 hours, it will take 1 hour. So, and if the program is actually memory centric, then that is the biggest advantage you get. Yeah, so what I tried to do here is just using some numerical values, I just gave you some insight into how cache can basically improve performance, but still memory holds the final word, okay. Out of these two components that you see in the recurrence equation, wherein one component basically talks about the L1 cache and the another talks about the thing that I missed something in the L1 cache. Now, between these two, now you see that this is the way we handle this. So, still the memory will have a much higher priority, okay. Now, there is a lot of study gone into architecture books, right, saying how to improve L1 cache, how to improve this blah blah blah, right. I do not find that as an interesting issue at all, because finally memory matters. If I have a faster memory, right, if I have a faster RAM and I have a faster interface, this is minuscule. So, why should I keep say I will improve, so how will I improve hit ratio? I will try to keep a big block, larger block, I will try to make my spatial locality and temporal locality more prevalent by having larger blocks, but then that will have a say, that will always have a say in when you want to replace, how much you need to replace. So, today that type of an analysis is sort of not necessary for an architect, it is my opinion today, right. So, you go and put as much as cache you want or you can, and that is better, right. And beyond some point you will not see that cache is going to improve your performance, because at some point if you keep on increasing the cache for smaller programs, right, for reasonable size program, your entire space at any point of time that locality of reference will be there in the cache, and it really does not matter whether all the other strategies that we are talking of, all the graphs, all the papers that we study, these are all useless in that context. Okay. So today I have a lot of real estate, I don't know what to do with that real estate, we are going with 7 nanometer, 10 nanometer. So I can put lot of cash, try to populate it with as much cash, but beyond some point this cash also becomes useless. And one other thing is that cache is a single block. Now what would happen is that I can't go and cut power to a cache. So then people try to look at banking, right. So the cache itself will be put as several banks, and each bank will have its own power rail. So if one bank is not utilized, because memory consumes more power than the normal gates, right. So if I am not using one bank, I can go and basically cut the power to that bank. Okay, it is as simple or as difficult as this. So right now let us now start talking about based on this cache hierarchy. Now I can extend it to L3, L4 till Ln. So based on this cache hierarchy, how are cache policies classified? Okay, now already we saw a write back cache with a write through cache, right? Did you right? You still remember that? Write back cache is that I write to L1 but memory will be different. So there will be this cache coherency issue. The latest value will be always in the cache, not in the memory. A write through cache is when I write something I will also write it there. So there will be no memory coherency. And there are certain classes of problems which are more read only in nature, right. That can be memory intensive but they are more read only in nature, which will actually benefit through write through cache, right. So that is one thing. And the point is that if I have minimum number of write throughs, if we have minimum number of writes, whenever I try to replace, right, I will try to not write lot back, right. So if I have a write through policy, then I can go and throw off anything at any point of time. So you save some time when you are trying to replace a cache block. Okay. So this is some understanding. Now let us look at two types of cache based on this L1 and L2 or multi-level cache. The two types are basically exclusive cache and inclusive cache. What is this exclusive cache? Whatever I store in L1 will not be there in L2, right. So if there is a location 1000, this is the RAM, and let me say I am bringing a location 1000 here, this 1000 will be first fetched to L2. Then it will be fetched to, say, let it be an instruction, it will be fetched to L1i. When it is fetched to L1i, this is removed. So a particular location, the data or instruction corresponding to a particular location will be in exactly one of the caches in that hierarchy, right. So that is basically called this type of a cache organization is called exclusive cache. By having an exclusive cache, what do you gain?
Hit ratio.
Huh?
Hit ratio.
What hit ratio?
Hit ratio.
How do you say hit ratio increases by exclusive cache? Hit ratio is basically a trace parameter. It is not where do you store. If I am accessing something again and again, it will be in L1 cache for sure. Whether that will be contained in L1, L2 cache or not is the story, right. If it is also going to be in L2 cache, then it is an inclusive cache. If it is just in the L1 cache, then it is just. So what are the advantages of exclusive cache? The main thing is that the coherency problem is just restricted to the one cache and the memory. In the L2 cache, the coherency problem can be multifaceted. What is there in L, so 1000 will be there in L1, 1000 will also be there in L2, 1000 will also be there in memory. Memory will store 100, L2 will store some 75 and L1 will store some 125. So there could be 3 different values for the same value. So what will happen is, when I am evicting, I have to take care that, so when I evict from L1, I go to L2 and then correct it there. And when I evict from L2, I go to the memory and then correct it there. So the cache coherency problem is now a large one. But so implementation wise, right, from the implementation point of view, I could have this 1000 in multiple memory location, and I have to basically handle that at every stage. So this is one very big problem when we look at this inclusive cache, wherein whatever is there in L1 will also be there in L2. So the content of L1 is a subset of L2, content of Lk is a subset of Lk plus 1. But here the intersection of L1 and L2 is phi, is an empty set, or Lk and anything else is an empty set. So if that is the issue, your cache coherency issue is just restricted to one cache. But the bigger problem of having an exclusive cache is that when I want to bring somebody in, I do not, so in the case of an inclusive cache, when I am trying, say let us say L3, L2 and L1, if I want to read somebody, first I will make an entry in L3, then I will make an L2, then I will make an entry in L1. So 3 entries have to be made when I am trying to bring, but in it is a case of an exclusive cache, I have to make only one entry. But the point is, when I am trying to replace somebody in L1, now I have to take him to L2 and bring somebody from L2. So when I want to bring somebody from memory into the L1 cache, first I have to bring him to, I can directly come to L1, from L1 I have to displace somebody and put that into L2, and if L2 is full, I have to displace somebody from L2 and put it into L3, and somebody is full in L3, then I have to move him to the memory. You are getting this? So as I keep on mentioning, right, I think I have mentioned several times, computer science is communist science, in the sense that if you gain something, you lose something. So these are the things. So for me, a cache coherency issue becomes very easy to handle in the case of exclusive cache, but cache replacement is equally complicated, right, and even fetching is fast here. So in the case of an exclusive cache, when I want to bring a location and that I have empty, my cache is empty, it is just one shot. But in the case of inclusive cache, I have to bring it to L3, then L2, then L1. But the point is, when the cache is full, then I have to do a big back off. When all the caches are full, I need to go and do a big back off. So you design caches in such a way that these caches do not get full very quickly, and that is why you get the performance, right. Now this whatever we have covered now so far is sort of, so one more thing I have to cover before I go to the multitasking thing. So last time I did talk about 3 important things, right. So one is called what we call as degree of multiprogramming. DMA caches interrupt, hardware interrupts. These 3 are basic building blocks to get what we call as the degree of multiprogramming. What do we mean by a degree of multiprogramming? The number of processes that we need to execute at the same point of time, right, processes that can be ready for execution. We saw issues like IO burst and CPU burst, right. I think I have covered this, but anyway I will cover it once more. So what is the IO burst? What is the CPU burst? They cover this or not? Yes. So tell me, what is the IO burst? What is CPU burst?
Like they are the times taken for input, output, and for CPU processing.
So no, it's not time taken. So what is the IO burst? So when a program is in execution, when a process is executing, it will go through alternating phases of CPU burst and IO burst. In the CPU burst, it will do a lot of CPU activities. In IO burst, it will do a lot of IO activities. IO being tremendously slower, we already saw with an example with the case of RAM. IO being extremely slow. By the time I do one IO, for example, by the time I press a key, it will do some 3 million operations. So CPU burst will be quite fast. So let us take process 1. When it does, I think we covered this, but anyway I will do that again. When it is doing its IO burst, right, that is do some amount of CPU burst. By the time it is doing its IO burst, several P2's CPU burst can be finished, P3 CPU burst can be finished, and so on and so forth. So many processes CPU bursts can be finished while one of the processes is doing cycle, right? So that's why, so when we look at the organization, there is a front side bus, there is a direct memory access controller, what we call as DMA controller. Here is the CPU, here is the peripherals, IO peripherals, and here is the RAM. Okay. During the IO burst of a process, this RAM and IO can directly act. We have already seen what we call as direct memory access, right? So the IO and the RAM can talk to each other, so the transfer of data can happen between the RAM and IO independent of the CPU, correct? And so, but then the CPU will do what? It will execute other processes. So the instruction and data for the other processes, if it is also there in the RAM, then the CPU cannot do anything. CPU has to wait. You got it? So CPU cannot do anything if the IO and the RAM and the if the instructions and data that are required for the next processes are there in the cache, there in the RAM. So that's why cache becomes very important. So I have a cache. So when P1's IO burst is happening, the instruction and data for P2, P3, P4, P5, the subsequent IO CPU burst of these programs will be there in the cache, and that can be ensured because of spatial and temporal locality, right? So the CPU can be using that and keep executing the CPU burst of other processes while one process is doing its IO burst. Are you getting this? So here this means your CPU and the IO can basically happen together. So this is actually called as cycle stealing in computer architecture policies. Cycle stealing is when an IO cycle is happening, I can steal that cycle and do computation, right? So I am hiding the communication overhead by merging it with computation, and this is possible because of cache, right? And also that question that how will I implement the round robin scheduling, we have already seen, right? What is round robin scheduling? I take, then I pull you out, then put him, and so there is only one CPU. Pulling out will be done by the operating system? No, it is not done by the operating system, because operating system itself is a software and it can't execute to pull you out, because there is only one CPU. So when you are executing, there is a timer alarm that is set which will pull you out and put the next fellow. So this is one very, very important question that you will be faced, you will be asked, you will be facing any interview committee. So don't flunk there, they will crib me, okay? Right? So you all understood very clearly? So this is, and so DMA cache and the hardware interrupt together, right, work in sync to basically ensure that multiple processes can be executed in a round robin fashion, okay? Cache is all about, I have an address, I am storing some bit as tag bits and some bit as index bits, correct? Some bits I use for mapping and some bits I use for tagging, right? Now, which is the address you will tag? So if I look at, so let us go back to the address space. So there is a compiler which generates some logical address that gets added with the segment base to get what you call as effective address, and in the presence of paging this goes through a page translation mechanism, I get a logical address, I get a physical address. So a logical address plus segment base gives you effective address, that goes to a page translation and I get a physical address, right? Now what is the address that I will be using for caching? Can I use the effective address? Should I use the physical? What are the advantages? While I am doing the page translation, I can also start looking at the cache if I use the effective address, right? Because the moment I get the effective address and I use effective address for tagging the cache, for accessing the cache, so I can basically use, the effective address for, I will start doing the cache access here itself, and if I get a hit, Golimar, I do not want this. If I get a miss, by the time this cache access, this page translation will also be going in. So the page translation will be going through that translation look aside buffer, right, TLB also. So this will go through the TLB and then there will be TLB miss, so much mess can happen there. But while this is happening, right, till a physical address. So if I use a physically addressed tag, then this becomes sequential. First I have to do page translation, get the physical address, then do a mapping. So this is what this effective address is, basically virtual address. So I could have a virtually tagged cache or a physically tagged cache. Okay. So one interesting thing that I get when I use a virtually tagged cache is what? I can start accessing the cache the moment I get my effective address. I need not wait for the page translation to happen. And if I am getting a cache miss, throw it off. But if I get a cache hit, then throw that other part off. You can even stop that process. But if I am getting a cache miss, by the time I realize a cache miss, there will also be a TLB, and there is a TLB hit, then I can start using that. Then I can start fetching it. Okay. So this is the thing. So what would happen is, so this is one advantage I get if I have a virtually tagged cache versus a physically tagged cache. Okay. So I used a virtual address basically to go and look at this to entirely manage the cache. Now what is the complication here of having a virtually tagged?
We update something in the cache, you have to write it back to the RAM. So before that you have to translate it to the physical address.
Yeah. So if I have a cache miss, it's hell for me. If I have a cache hit, then it is heaven for me. Correct? If I have a cache miss, then I don't know, this is only a virtual address. Where in the memory it is going to be there, I don't know. Okay, so then I have to wait for the entire translation to happen, and then I have to go and map it and go back. Okay, so that's a big complication when I have a virtually tagged cache. So can I have this question? So we are touching 950. So can I have a virtually tagged, physically mapped cache? Right? I leave the story here. Can I have a virtually tagged, physically mapped cache? Right? You almost did the class. Okay, so her reasoning is correct, wherein if I have a virtual tag, I can do things in parallel, because already memory access is a crap, right? I'm into so much issues. It's a monkey. Now I want to access, I want to get rid of that whole thing in whatever best way. So I'll try to do all the best to see that my lot of concurrency happens, and this gives me a beautiful concurrency as you see here. But then the complication happens when I want to do a replacement. That's a nice thing. So can I have the best of both worlds where I can do this and that? Okay, so let us, can I have a virtually tagged, physically mapped cache, or vice versa? So just start thinking about it, right?